In this problem, we're asked to use Thevenin's theorem to find V0 of t for t greater than 0. We're going to utilize two problem-solving strategies. One is S-domain circuits, and the other one is applying Thevenin's theorem. If we look at our circuit there, we've got a dependent source this time, and we've got a voltage source. It's 50 U of t. Our problem-solving strategy, S-domain circuit, says first find the initial conditions. And if we look, we only have one source. It has a value of 0 for t less than 0. As a result, all initial conditions are 0. Now, step 2 of our strategy says draw the S-domain circuit. So here's our S-domain circuit, and we're going to analyze this using Thevenin's theorem. And if you remember, when we apply Thevenin's theorem, we remove a load from the circuit, the load, and here we're going to let the 2 ohm be the load because that's what we're looking for the voltage across. We're going to make terminals, or a port with terminals A and B. We're going to find a Thevenin equivalent looking back into those 2 terminals. And then once we have that, once we have V open circuit and Z Thevenin, then we'll hook the 2 ohm back up to that and calculate V0 of S. Now, we have a dependent source this time, which means we're going to have to solve for V open circuit and I short circuit. So let's first look at V open circuit. Now we're in step 3 of our strategy. We're now doing the analysis step. So here's our circuit for calculating V open circuit. We've removed the 2 ohm from the circuit. Now if we notice, for instance, this current has to be 0, which says that this voltage has to be 0. And that tells us then that Vx prime of S is 50 over S volts. Now, to calculate V open circuit, we're probably going to need to apply KVL around the outside loop. First, let's go through and let's solve for the current. I'll call it I of S in that loop. And if we write a KVL equation for that, we'll get 0.2 Vx prime of S is equal to 1 over S plus 1 times I of S. And now we can substitute this in. So we'll have 10 over S is equal to 1 over S plus 1 times I of S. And then if we go in and solve, we'll get I of S then is 10 over S plus 1. So that's I of S. And then now, if we apply KVL, we won't go around the outside. What we're going to do is we're going to go around this loop that's the dash line, and that's because we could go either way. I decided to do this one because I know the current, and it's 1 over S times that. So VOC then is 50 over S minus 1 over S times I of S. Okay. So if we go around by the dash line, VOC is 50 over S minus 1 over S times I of S. And if we go through and do the algebra, we get 50 times S plus 0.8 over S times S plus 1. So there's the open circuit voltage. We've completed that calculation. Now we need to calculate the short circuit current. So again, we're in step 3. Here is our circuit for calculating the short circuit current. Notice we've got terminals A and B, we've connected them with a short, and now we need to look at how we want to analyze this. Let's use nodal analysis on this one, and let's pick the bottom node as a reference. So that tells us this node voltage. Now if we look at our circuit, for instance, if I define this voltage as VA, and if I go around the loop comprised of this element, and back around here, I can write the following equation: VA of S minus VX double prime of S plus 0.2 VX double prime of S equal to 0. That tells me that VA of S is 0.8 times VX double prime of S. So what we'll do now, since Vx of S is this, I'm going to first calculate this current. If we look at this current that is, I'll call it IA, which is VA over 1, it's 0.8 times Vx double prime of S. So I'm now, since I know this current, I'm going to apply KCL at this node. Okay, and that's because I know IA leaves this node. So for instance, if we do KCL here, we would have Vx double prime of S over 1 over S. Then we would have Vx double prime of S minus 50 over S divided by 1. And then we'll have this current, which is IA, which is 0.8 Vx double prime of S equal to 0. Now, if we go through and solve this for Vx double prime of S, it becomes 50 over S times S plus 1.8. Now, if we're going to find I short circuit, we're going to now need to apply KCL here. Okay, so to find KCL, we need to apply KCL at that node. So if we do, we have I short circuit leaving, and entering, we have IA, which is 0.8 Vx double prime of S. And then this current is Vx double prime of S over 1 over S. And then I short circuit of S then is 50 times S plus 0.8 over S times S plus 1.8. So now we can calculate Z Thevenin as a ratio of V open circuit to I short circuit. We have 50 times S plus 0.8 over S times S plus 1 divided by 50 times S plus 0.8 over S times S plus 1.8. So then Z Thevenin becomes S plus 1.8 over S plus 1. So now we've completed calculating the Thevenin equivalent. Now we're going to reconnect our 2 ohm load to the Thevenin equivalent. Okay, and again, here's VOC, Here's Z Thevenin. So now using voltage division, V0 of S, we have 50 times S plus 0.8 over S plus 1, and we have 2 over 2 plus S plus 1.8 divided by S plus 1. And if we manipulate this algebraically, we come out with 33.33 times S plus 0.8 over S times S plus 1.267. So now that completes step 3 of our problem solving strategy, where we get a ratio of polynomials for V0. Now for step 4, we're going to do the inverse transform. So we have V0 is 33.33 times S plus 0.8 over S times S plus 1.267. And the partial fraction expansion for this is K1 over S plus K2 over S plus 1.267. So K1, we multiply through by S and let S go to 0. So we have 33.33 times S plus 0.8 over S plus 1.267. Evaluate S equals 0. That gives us 21.05. And then K2, we multiply through by S plus 1.267. And we let it S equal minus 1.267. We get 12.286. So we have V0 of S then is 21.05 over S plus 12.286 over S plus 1.267. So then V0 of T is 21.05 plus 12.286 e to the minus 1.267 T U of T volts.